Hey folks, welcome to week 4. We are getting closer and closer to talking about statistical inference, that thing that lets us determine if two samples are different from one another or if there are significant associations between different variables. In this video, we're going to talk about z-scores. I'm going to do something a little different in this video. In previous videos, I started with theory and then moved towards examples. I was thinking about it, and it's not really a natural way to learn things. I'm not the first person who's thought of this, but I figured I'd give it a try in this particular video. What we're going to do, instead of starting with theory and then moving to practice, we're going to do things the way you kind of learn things when you were younger. You do them. You work with them for a bit, and then you start to learn a little bit about how and why you do those things. So what that's going to look like in this video is what you see here. We're going to start with how you can convert raw values to z-scores, and how you can convert z-scores back to raw values. We will then define what a z-score is, and then talk about how and why we use z-scores. I do have a note that I want to make later in this video about Likert scales and things that are related to Likert scales before we get to talking about the next steps in the course. Alright, if this approach is too disorienting for you, or if you find that it works really well for you, please let me know. Shoot me an email, and that will help me to understand how I can move forward with other videos in this course. If I have some value, let's just call it value, and that value is 40. If I happen to know that for the population that that value came from, the mean for that population is 35, and the standard deviation for that population is 4.5. With that information, I can calculate a standard score, or a z-score in this case. The way I do that is I'm going to take the value and I'll subtract the mean from that value. And then I'll divide that whole quantity by the standard deviation. And the result is a score, a z-score. Now we can do this with other numbers. We can kind of get a sense of how this might change as values get further and further from the mean. So if instead our value was 50, we can take this same calculation, and here we see we get a much larger z-score. So it seems like the further away from the mean a value is, the larger its z-score might be. Well, let's test that out. This time, I'm going to give myself a very low value. I'll give myself a value that's, instead of 15 points above the mean, I'll give myself a value that's 15 points below the mean. So my value is going to be 20. And if I run that calculation, now I get the exact opposite number, right? So it seems like if a value is less than the mean, we get a negative z-score, and if a value is greater than the mean, we get a positive z-score. The further away that value is from the mean, the more positive or negative that z-score is. Well, what happens if we have a value that is the mean? Well, you probably guessed from looking at the formula here, you're going to wind up with a 0. Because if the value equals the mean, value minus mean is 0, and 0 divided by any number is 0. Well, that's easy enough if we have a single value. We could type it into a calculator. We could use something like a Jupyter notebook here. Don't worry, you don't have to use Jupyter notebooks in this class. But we could put this into a spreadsheet in Excel or in Google Sheets, and we could do this calculation. But when we're dealing with real data, you could have hundreds or thousands of values, and that would be incredibly tedious to have to do that all by hand. Luckily for you, In SPSS, you don't have to do it all by hand. So calculating z-scores for one or a handful of numbers is relatively easy. But if we had to do that for hundreds of numbers or thousands of numbers, like you might have in a large data set, it becomes really unreasonable. While calculating z-scores for individual numbers is possible and even easy for small numbers of values, it can get really difficult to do and really just not a smart idea to do when we have larger data sets. If you have a set of data that has hundreds or thousands of values in them, it's really an impossible task to go through and calculate those z-scores individually. So yes, you can calculate z-scores for individual numbers. And while you could do that with hundreds or even thousands of numbers, like you might have in a real data set, it's ill-advised. Doing that many calculations by hand leave lots of opportunities for typos and other sorts of silly missteps. So instead of doing that, because you have access to SPSS, you can let the machine do the work for you. I'm going to go ahead and import a familiar data set here. If you have questions about how I'm importing these data, please take a look back at one of the earlier videos so that you can get a better sense of how to do this, or reach out to me directly over email. Now that we have our data read in, if I wanted to calculate a z-score for age, sleep hours, physical activity, or caffeine intake, for example, I could hit the Analyze tab, the Descriptive Statistics section, and instead of frequencies, we'll click on Descriptives. Here you can select the variables that you would like to calculate z-scores for. We'll add those variables in. And the key here is that you need to check this box that says Save Standardized Values as Variables. By checking that box, SPSS knows that it should go through, calculate those z-scores, and then create columns filled with z-scores for each of the columns that you selected. So we'll hit OK. And now you can see we don't just have age, we also have z age, and not just sleep hours, but we also have z sleep hours. And so it's gone and calculated z-scores, which you see in these columns. And those were calculated the same way that you saw me calculate a z-score just a moment ago. The value in the original column, we take that value, we subtract the mean for that column, and then we divide the result of that by the standard deviation for that column, and that gives us a z-score. Now, there is something I wanted to note for you here. If we hit Analyze, go to Descriptive Statistics, and this time actually calculate some descriptive statistics, we're going to go ahead and select the original columns, and we're going to select the z-score columns. We don't need the frequency table, but in statistics, let's just make sure we have the mean selected and the standard deviation. Now, what's interesting here is that when you look at the original columns for age, sleep hours, physical activity, caffeine intake, for instance, these uh, statistics, they sort of make sense. You have an age of 40.41, that's the mean. For sleep hours, the mean is 6.722, and they all have their standard deviations.
But when we look at the z-scores for these variables, all of the z-scores have a mean of 0 and a standard deviation of 1. That is an important aspect of z-scores distribution, and we're going to talk about that a little bit more in the coming slides.
Let's just think for a moment about what we're doing when we're calculating a z-score, what that z-score actually means. If we take a look at the formula, that z is whatever value minus the mean for that distribution, and then that difference is divided by standard deviation. So for a moment, I'm just going to take you back to like third grade, fourth grade, when you're first starting to deal with division. One way that we talk about dividing things, if you have 6 divided by 2, your parent, your teacher, your older sibling, older cousin may have asked you, well, how many times does 2 go into 6, right? How many 2's can we get out of 6, right? That's another way to think about 6 divided by 2. If we put that same logic to this example, it can be, I think, informative. What we have is the distance between an observation and the mean, and we're asking how many standard deviations can we find in that distance. In other words, a z-score is the number of standard deviations that a value is from the mean. Z-scores have other interesting attributes. The distribution itself has some really convenient properties, like being normal. We'll talk about what normal means exactly in the next set of videos, but for now, just know that if a distribution is normal, we can know the exact shape of the curve. There's actually a kind of scary looking function that you can use to figure out all the values in that distribution if the distribution is normal and you know its mean and standard deviation. Another thing that's really useful is that the area under the curve equals the probability of the values that are in that area. Now that may not mean a ton just yet, but wait for the next slide. I promise you, I'll try to make that a little more clear. Z-scores also allow us to make some comparisons across different groups. And we can do that because, as you saw before, the mean of z-scores is always 0 and the standard deviation is always 1. So it effectively puts the groups on the same scale so that you can make a fair comparison. Because the area under the curve tells us something about the probability of values in a given range, we can say something about the likelihood of observations in that range, and we can use that to make judgments regarding statistical questions. So how do we actually use these z-scores? We know how to calculate them, but like I said, those z-scores are associated with some probability of a value related to that z-score. I want to say something more specific, but I need to show you something about those z-scores first. But let me say this. One of the easiest ways to go about using z-scores is to use a z-table. These are tables that folks have worked out that tell you the probability of finding some values associated with that particular score. You need to read the directions on that table carefully. And this is why I was hesitating to say something more specific earlier. You have your z distribution. Again, your mean is 0, the standard deviation is 1. So you calculate a z-score. And then you go to that table, and the table can tell you a couple different things. Depending on the table, that table may give you a value that tells you the probability of finding a value between the z-score you calculated and the mean of that distribution. Other tables might tell you the probability of finding any value larger than the z you calculated. Yet others may tell you the probability of finding a value that is less than the z you calculated. This is also something that you can calculate in SPSS. So on Blackboard, you should have been able to download a PDF file called ztable. When you open up that file, it'll look like this. When I mentioned in the previous slide to pay attention to the directions, I mean particularly to pay attention to the pictures like this and the information above that tells you this shaded region, the region between the mean and z, is what this column is giving you. It's telling you the probability of finding a value between z and the mean. Whereas this column is telling you the probability of finding any value greater than z, because the shaded portion is to the right. Many z-tables are different, so please, please, please make sure to check to see how that particular z-table should be used. But once you figured that out, the only other thing you need to know is what your z-value was, what that z-score was. You take the z-score and you'll go down that left column until you find it. In our earlier example, we had a z-score of, I believe, 1.13. So I'm going to have to scroll for a little bit because these are just 0.11, 0.12. Let's keep scrolling. All right. For a z-score of 1.13, the probability of finding a value between the mean and that z is 37.08, and the probability of finding a more extreme, a z-value greater than 1.13 is 12.92. And that's it. You look for the z-score, and then you look across the row to, in your case, either find the probability of a score being between the mean and that z, or the probability of finding a z-score, or rather a value with a greater z-score. I mentioned that you can also use SPSS to calculate the probability of finding a value less than your particular z-score associated value. Well, what do you do if you want to find out the probability of finding a value greater than that z-score, but you can only work with SPSS to calculate your values? You don't have a z-table. Well, remember this. We're talking about probabilities of finding a number. Since the z-table, since the z-score goes from negative infinity to positive infinity, it encompasses all values. These are all the values that you could possibly get. And so the total area under the curve is 1. The probability, in other words, of finding any value is 1. You will absolutely find some value if you have a number. So we can use that to our advantage. We'll use logic to find the probability that we're interested in. If we only have the probability of values less than a particular value, we'll say that those are p, and then the values that are greater than that value, those are going to be 1 minus p. All right? So I just want to show you how you can calculate the probability of finding a score that is less than the value that you have for a particular z-score. You can do that in SPSS, but it requires a little bit more work. Let's say we want to calculate that for values in z age. What we can do is we can go to Transform, Compute Variable. When you do that, this screen will pop up. Now we're going to name our new variable, and we're going to name this p lower age, right? Because we're getting the probability of finding a value that is lower than the one we have for a particular z-score in the column age. All right? And so since I'm working with the z-score, I'm going to go ahead and get the z-score age. And that's what I'm going to use. Now, there's a function that we need to use. It is CDF dot NORM, CDF norm. We're going to give it parentheses, and then we're going to give it the name of the column that we want it to calculate the CDF, or cumulative distribution function, for. And that's z-score age. Now we need to tell CDF a few other things. We need to tell it the mean. Since this is a z distribution, the mean is 0. And we need to tell it the standard deviation, which again, since this is a z distribution, these are z-scores, the standard deviation is 1. Alright? And now we're going to click OK. And now we have another column, p lower age. And here we have the probability associated with the z-scores in z age. Now, you can go ahead and you can play around with that CDF norm function. I think you'll find that there are some other interesting things that you can do with that and raw scores.
Okay, that's all we're going to talk about for z-scores in this video, but I wanted to take a moment to talk to you about data types again. We spent a lot of time on data types early in the quarter, and it's important because the type of data that you're working with tell you what types of tests you can use, what things you can do and infer from those data. Likert scales are scales that go from 1 to 5, and you may be familiar with a scale like this. After eating in an establishment, you get a survey, and the survey questions say things like, on a scale of 1 to 5, with 1 being the worst, 5 being the best, how would you rate the friendliness of our staff? And they'll have several other questions like that. These are rank ordinal data. However, many psychologists treat them as though they were interval level data, and they run analyses on those data, again, as though they were interval level. There is a living debate about what we should do with these Likert scale data and their kin, right? How should we treat those data? If we treat them as though they are interval level or ratio level data, that means we can use lots of different statistical tests, calculate lots of different descriptive statistics about those data. If, on the other hand, we treat them as though they're rank or ordinal, well, that limits which tests we can do and which statistics we can calculate. I'm going to leave a few links for you so that you can get a few other opinions, hear a little bit more about this discussion about how we should treat Likert scale data and their kin. And hopefully you'll have some questions for me that we can discuss over email. Next week, we'll be talking about the normal curve, what it is, and why it matters. And that will be the last thing before we start getting into inferential statistics and how we test hypotheses. Take care.